Thanks for the opportunity of giving a talk in those weird times. My name is Boaz, and this is a joint work with a group of students of mine. And I will state how much they did. I'm the presenter here, but really, my part in that is mostly the vision and helping with bringing coffee and pizza in COVID-19 time. Anyway. I'm going to give a presentation about a concept of Wi-Fi from space. But before that, I'm going to give a little bit on the SATTLA project. Sadly, not all the what we planned to have is actually in our current satellite, which is in ALBA in integration. But the vision, hopefully, the entire vision I'm going to present here, going to be in the next satellite. So let's start. So basically, the notion of SATTLA is an educational program of how to make students involved in NewSpace, how to make, instead of a faculty project or an industry or university project, how to make a blend of everything, mostly interdisciplinary. Most of us are not engineer of any sort, and we cannot solder anything. The main goal is to have a laser communication link for extremely high into a gigabit per second, gigabit per second laser link to towards a picosatellite. And as a partial steps, we think of doing some sort of Wi-Fi. This is going to be the main topic of this talk, and also the concept of multi-ground station as a concept where you not necessarily have your own ground station, but you use thousands or hundreds of other people, other organization ground station. In preparation or integration, actually SATTLA 1 is a 1U satellite, which is already in the ISS, ready to be launched, hopefully in the coming 3 or 4 weeks, sometimes in early November. I will elaborate more on it. SATTLA 2 is our current in integration in ALBA facility 2P satellite, and then in our thoughts and in our COVID-19 engineering, our SATTLA 3, which is more of a remote sensing serious satellite, and SATTLA 4, which is the even numbers are more of a U standard, more of a serious satellites, and the odd numbers, and the even numbers are serious research stuff, meaning we try a lot, not necessarily we'll get it all in the first time. So SATTLA 4 should be a Wi-Fi video, real-time video transmitter and an IoT service from space. And what you can see here is the SATTLA 4 or SATTLA 2, sorry, laser beam from about 10 kilometers from the university, and this is the little satellite here on the image. Right. So the goal is to have a laser communication, laser link from space. Obviously, that requires an extreme accuracy from the attitude control determination in a system, and something which should be significantly better than a sub-milliradian accuracy, and have the ability to do a dynamic tracking of not star tracker as such, but mostly a ground tracking towards sub-milliradian tracking, which is a quite complicated issue on a large satellite, but on a tiny satellite is a big deal. And the ground station point of view, we have a kind of a telescope which points to the satellite, and hopefully using fast avalanche photodiode can interpret the pulse of lasers towards data as if it was a fiber. This is a little bit few words about SATTLA 1, which is currently in the ISS. Hopefully it has Raspberry Pi as their kind of, if you would, the the main payload boards, two of them for redundancy. We're not sure it's going to work. Each has their own 8 megapixel cameras and OpenCV and Python. It has an array of LED. You can see that here. Hopefully, with an amateur telescope, you should be able to detect that and have some interesting experiments with GPS, IMU, and time of flight RF ranging from that. And we have some sort of option to upload Python scripts to that satellite. So some of the interesting experiments we're not fully developed them because we said, that requires good programming and hopefully, and we should. There's no reason to do that before we have that satellite working. SATTLA 2 is a 2P project currently in the Alba facilities. It has 3 reaction wheels, as you can see that here. It's actually brushless motors coming from high-grade drones, and it should be able to perform 3 ASICs accurate aiming towards kind of LED or a laser beacon from ground. It was built, as others mentioned, in a COVID-19 engineering, a lot of 3D printing, a lot of improvising, and we're not fully sure all the things will work. But we do count on LoRa, mostly UHF, and then LoRa on the S-band, and I will elaborate a little bit more afterwards. In a nutshell, we're not an expert. We know very little on space, and we're not a very engineering group. We're more of a research group that loves toys. We're grown-ups that love to play with toys and gadgets. And for years, we've been playing with high-altitude balloons. Most of our practical experiments are to take our electronics and put it into a near space condition with a balloon, and hopefully see if it works. This is the way we practice stuff. It's more fun. Sometimes it's depressing because not always it's been working, but a few times we got it right. And using that kind of a notion, we've been able to hack Wi-Fi towards from 100 meters average distance towards 30 kilometers, and that helped us to bring those kind of little drones. This is like a kite that has tiny little motor and autonomous flight back towards the campus. And 1 out of 3 or 4, it's actually goes all the way back. So this is our testing facility. This is actually the drone bumping into the university fence, but we got all the way back. This is me doing low-tech high-altitude balloon payload. This is while the COVID. This is on April, where I'm teaching other universities and other high schools of how to do a payload with a Wi-Fi transmitter, a long-range Wi-Fi transmitter, a GPS, flight controller, which is the black part, it's a Picosat on the left, and no soldering. So just by duct tape and USB connectors. And the electronics cost about like $200. And a lot of universities and other schools are doing that. And this is actually an image of, eventually I got it to work. This is actually an image taken from about, let's stop that endless thing. So this image was taken about 60 kilometers, 60, from the university, 10 kilometers up. And it gives us, this is using standard Wi-Fi. So how do you, so the big question, the big topic I want to share here is how you take standard hardware of Wi-Fi and you benefit it, you push it from, say, a few hundred meters towards, 100 kilometers, and in a few slides, 1,000 kilometers. So the idea is that you don't need to do any electronics yourself. If you take commercial drones, two of them which are very known for the long range, or there are Mavic 2 Air and the 𝗖𝘁mě 𝗨𝘁. They can do 10 kilometers full HD transmitter on a standard antenna. If you use FCC wise, if you use directional antenna, like you can see here on the image, you can go to 100 kilometers. It won't necessarily be, you know, flawless video flow, but in most cases you would get a proper video. But you do need some sort of hacking. A very good software, I cannot emphasize enough how helpful they are the easy Wi-Fi broadcast and all their forks on the internet. I will point to a certain fork of them, which is extremely helpful to hack the Wi-Fi. Basically, it detaches the need from having your client being associated with the router. The client basically transmit, and any associated router, not as unassociated router, may be able to transceive that and get the information. So this is a Raspberry Pi 3 connected to Wi-Fi cards, and basically with forward error correction, being able to perform high altitude balloon from, say, 100 kilometers. Some sort of practice on the right-hand side versus theory. So if you take theory, 30 dBm Wi-Fi FCC transmitter with 8 dB gain, you do the math, and you get 160 dB budget link. That should be able for allow you to have some sort of low resolution, I would say 1 to 2 megabits per second from space. If you take practice, and this is the our approach, you take whatever you can find on your shop as a Wi-Fi card, and you plug it in. You have a standard TX antenna, and then and a standard TX a receiver antenna. And the sensitivity is not as good, but in that practice, we've been able to have a relatively good video link for 270p, whatever. It's like not full HD, but good enough for 30 kilometers. And you get an extra 36 dB to spare. You do the math. You divide it by by 6, and then you do to the power of 2, and this is shows the applicability of doing it from low Earth video. And this is basically the numbers here. You can see the GPS, the signal strength, the height, and keep in mind that in those high altitude balloons, basically you are very close to the horizon. Although you are maybe 10, 20 kilometers up, you are more than 100 kilometers away, and your 2.4 gigahertz Wi-Fi transmitter is fighting the thick atmosphere it needs to cross. And in the path of a satellite, that things are not as hard. So this is how you push it towards low Earth orbit. So basically, the here link, we were not using it on high altitude balloons because they're quite expensive, but they can do 20 kilometers easy on FCC on Wi-Fi link. You have two HDMI, so you can do both selfie and the other camera transmitting it together. Bi-directional antenna, you can get a factor of 10. Okay, so this brings you to around 200 kilometers. To push it all the way, you need a good forward error correction, and I cannot emphasize enough how open HD is helping with that. Their community is amazing. They're doing amazing Raspberry Pi based piece of software that helps you do all the forward error correction, all the two-way channel of controlling your drone or your whatever your satellite from the ground station. And they're doing an amazing job. Recently, we found a work we were not aware of that in 2016, just lately, I think it was a year back, the world record of having a continuous, perfectly Wi-Fi video was break, and they got over 300 kilometers, allowing minus 70 dB. So obviously they can do 10 times that. And we were able to do the same experiment with cheap, significantly cheaper and more affordable communication, and using FCC standards, and having about 100 miles or 160 kilometers of a video link, using standard hardware. You can see here the antenna. Right. So pushing it towards a little bit more than 500, because obviously you think of a 500 kilometer, but most of the passes are more in the neighborhood of 1,000. This is hard. So the last 6 dB are kind of hard. A rich organization solution will be having a good ground station, a big ground station antenna. Those are expensive. And having a very good SAT antenna. Those two solutions are complicated because it requires a lot of engineering. The amateur solutions, or the good programmer solution, would have putting a lot of emphasis on good forward correction and playing with the parameters of the Wi-Fi, and do a dual solution of both 2.4 and 5, because the pros and the cons of both of them are kind of weather dependent. So you might want to have them together. We found a work just recently. I actually, frankly, I haven't read it through. We know that in 5 years back, the use of Wi-Fi were shown almost 400 kilometers video link. And the way they did it is they basically took commercial off-the-shelf devices, and it worked for them. So I would say that a better Wi-Fi, newer Wi-Fi devices with some better ground station could help mimic their solution. And here is in a nutshell, this is the only important slide you need to remember. So nothing about us, or very little about us. First of all, Amazon is currently allowing AWS ground station service. We are with, initial cooperation with them to test 2.4 LoRa, 2.4 gigahertz LoRa with them on their amazing, huge, extremely expensive ground station. They have a few ground stations spreading around the world. You can pay as you go with them. And on an S-band, it shouldn't be more very expensive. So if you have your packets and you want to pay for having proper images, and you don't have the time or the efforts to have a serious ground station on your university, this might be a very good solution. We are working strongly with the amateur, the radio ham amateur, to have a $100 ground station. This is LoRa based, and this should be able to help us to do some sort of LoRaWAN gathering of information. Another concept we play with is to have a telescope ground station, a laser ground station. This is complicated topic. It raised a lot of interesting, complicated problems. So I will bypass that and just say that if you have a telescope, if you have a robotic telescope, and you can record the video with the and record the data with a with the avalanche photodiode, and you just can you maybe get a few dollars from someone just said, can you follow my satellite? I just want to blink few seconds of laser. That might be a very good cooperative way of having your satellite LED or laser transmitting through unlicensed band. And obviously Wi-Fi, the lowest point. Wi-Fi is the most suitable device for multi-ground station. So trying to summarize things. So obviously one big question that I have a master student of mine keep asking, whether should we go for the lower frequency 2.4 or the 5. Obviously, 2.4 has a lower space loss, but it's an easier to hack and amplify. And there's a way more experiment than that. But the 5 frequency seems to be more suitable. A, you can have better antennas, both on the ground and on the space. B, you can you have higher bandwidth. And most long range drones use 5, and there are serious people there. And why not use both? If you get a good alpha card, you can have them both. So it's not actually a question. We've been actually took us quite a while to understand that you don't really need to do the comparisons, and one most advanced and modern cards have them both. Yeah. So last slide. We're currently in our ground station. Even in COVID times, we plan to do some sort of ground experiments towards 10 and 30 kilometers for ground experience for Wi-Fi, for long-range Wi-Fi. And this could be an open link for others that want to work. In early November or late October, it's not yet given the time, we plan to do a high-altitude balloon experiments to try and have a solid 200-kilometer video link on Wi-Fi, and on standard Wi-Fi, meaning standard COTS, not amplified Wi-Fi. And yeah, and currently we're working on the notion of 3P SAT with hopefully next year will be launched from Alba facility as well. And there's a lot of issues to do: the antenna, the attitude control, the power to deal with the Wi-Fi, and the also the notion of multi Wi-Fi like or ISM like ground stations to cooperate with others seems to for us to be like a very good common ground for cooperation. So we are open for cooperation. We're not a business of any type. Let me just summarize that to build yeah, it takes a small tribe to build a Picosat, mostly in COVID-19 times. I want to especially give my deeply thanks to Amit and Ronnie and Revital and Aaron, Michael, and Liran, that together they're all students. They all drank a lot of Corona beer in those crazy times, and combined they've been able to build this summer two satellites, and it's an amazing job. Thank you very much.